Hi guys, Will here. Today we'll be talking about finite volume second order solutions to the steady state temperature distribution for a uniformly heated disk. Our line is that we'll be going into our problem introduction and background, numerical methods, validation convergence studies, key results, and then conclusions. Finite volume methods, as a bit of background, use a bit of Gauss divergence theorem, where one part of this information from a nearby cell is going to be used at the current cell to get a flux estimate. First order approximations are typically limited to the nearest neighbor cells for the flux adjustment, which can lead to over-diffusion. In other words, they neglect flux contributions from further neighbors at k is equal to 2, 3, 4, where k is like that set of neighbors that you're looking at. The goal is to use a second order finite volume solver to improve some accuracy in that. For our method, we'll use a uniformly heated disk then to compare our second order and our first order comparisons for the FVM finite volume method. A numerical formulation is given in the middle, which follows from Gauss divergence theorem, where J, in this case for each of the summations, is going to represent the current cell that is not I, where I is the center, and J is the nearby cells that you're going to do for the approximation. Each neighbor level for this summation that you see on screen will be given as such. Level 1, which is the nearest neighbors, will be a weight of 1. Second neighbor over at level 2, k is equal to 2, his weight is equal to negative 4/3. And third neighbor level over, at k is equal to 3, the weight is 1/3. So if level 3 does not exist, i.e. near the edge of a circle, we swap over to our first order methods for the approximation for those near edge circle pieces. And for this disk, q is equal to 1, there's 2000 elements, and the radius is equal to 1. Gauss SOR is used to resolve each of our iterations here. So we assume that the circumcenter temperature is approximately the average element temperature. We have uniform heat sources, and we neglect higher order terms present within the gradients between each of these cells. So for each cell, we have the following weighting here, where we take into each of these elements distance t sub ij and a temperature of t sub j for each of these nearby elements, by lengths of L sub ij, and elements with q sub I, a sub I for heat and area, and the T sub I, which is the temperature at I. This is first order because we're only looking at the nearby cells. Second order, we can go ahead and get the information from nearby cells here, which can go ahead and illustrate our jth neighbor up to k is equal to 3. So 3 neighbor sets instead of 1 for second order. Boundary conditions is T sub ghost is going to be the negative of the temperature at I at the edge, where it's a first order-ish, if you can imagine, because we're only taking in the boundary condition at the first level of cells. Our numerical method for its benchmark is going to be an analytical Laplace equation for the uniformly heated disk, which is as so. This will be used for comparison and benchmarking in numerical results. For our results, left-hand side is second order numerical solution, right-hand side is the analytical solution. Left-hand side numerical solution has some weird stuff going on at the edge because they're not being satisfied correctly with k is equal to 3, because there's some influence from the cells that are nearby that take a really big distance of fluxes that are just simply not available at the edge. But we see that from the left-hand side and right-hand side, they are very much convergent and almost exact. For results in comparison, in red is the analytical solution, blue is numerical solution. Left-hand side is first order. We see that it's going to be overly diffuse and it doesn't predict the analytical solution very well. However, on the right-hand side, we see that using the second order difference, we get much closer results. This is the middle line solution slice for all y's for the temperature. Here, for our error for the second order on the left-hand side versus first order on the right-hand side, we see that both methods are convergent, and both of them take roughly the same amount of iterations. However, for second order, each iteration takes a significantly longer time than the first order, because you're considering 3 sets of neighbors rather than 1 set. So for our improved accuracy, or for our conclusions, we have improved accuracy for the second order finite volume solver. We see reduction in over-diffusion with the second order, and better alignment with the analytical solution. The only problem, though, is that the second order closely matches to the first in iteration count, but each iteration takes more time. Thank you. That's the end of my presentation, and if anyone has any questions, please come up and ask. Thank you and have a wonderful day. Bye-bye.